Thank you very much for inviting me, and thank you for staying up for the last talk of the day. So I'm going to be talking about a statistical learning theory approach to causal inference problems. Primarily, I'm going to be focusing on a single paper, which is joint work with Dylan Foster, who is a postdoc here at the IDSS. But I'm going to be giving a brief overview of other papers in the area. So the motivation of the work is that machine learning is infiltrating more and more decision making. So we see that in multitude of domains, like in business, personalized medicine, or law, people are trying to use machine learning to answer a lot of decision questions. For instance, how would you offer personalized discounts, or how would you offer personalized drug therapies, or what bail should a judge set? The problem is that most of these decision-making questions require understanding of answers to causal or counterfactual questions. So what would happen if we change the existing policy that we deployed in the data that we collected and did something else? While most of machine learning methods are typically targeting prediction questions. What would happen in the future if we continued the same treatment policy as the treatment policy we used for the data that we collected? And so you might think that these two points seems to be implying that machine learning is not a good fit for causal inference, but what I guess we'll try to show in this talk is that many times we can still get a lot of benefit from using machine learning in decision-making or causal questions. And for instance, many times we can estimate causal ML models as long as we use auxiliary models for debiasing the pure predictive models that we could have fitted if we deployed machine learning in a naive manner. So there is some hope of combining multiple machine learning models in an intelligent way so that you can get a sort of causal-looking model. So the goal would be to develop a general framework for such machine learning with nuisance models. These auxiliary models are typically called nuisance models. And two main points is that there's a lot of benefit from econometrics, from combining techniques from both econometrics or semi-parametric statistics and machine learning. And one is like from the field of econometrics, there's this very nice notion of Neyman orthogonality that is typically used in a lot of semi-parametric statistical theory. And we'll see in this talk that there is a nice way to combine this notion of Neyman orthogonality and generalization bounds that people typically try to prove in machine learning. And on the other side, what we'll hopefully show is that we can phrase a lot of causal inference questions as generalization bound questions and apply a lot of the recent results in machine learning and in statistical learning theory, and get guarantees for causal inference problems that are meaningful for people working in causal inference. So I'll try to highlight the main ideas of the framework through a series of 3 examples, and then I'll present the more theoretical formulation. So as the first example, let's try to see to look at the problem. Suppose that you are trying to estimate how demand of a product changes as a function of price. And suppose that you were a data scientist in a company and someone came to you with historical data of purchase and demand and price, and they asked you, what is the function of demand as a function of price? Right? And these are the data points maybe you had, and if you're sort of like maybe a beginner data scientist and you know some of machine learning, what you might want to try to do is to fit a model that predicts demand from price, right? And then say that this model that you fitted, maybe using machine learning, is the model that of how demand changes with price. And say you use here some sort of like maybe even a linear model. You fit this linear curve through your data, and it actually has a very small mean squared error. The residuals are very tiny. You do maybe some cross validation. You also see that their out of sample loss is very small, and you say that this is the demand as a function of price, and then you go to the person that asked you to do the task and says we should increase the price to to infinity because that seems to be maximizing our revenue. The problem is that you obviously made a big mistake here in that in trying to solve this task, you forgot that typically price changes in anticipation of demand. So there's a lot of other types of variables that would cause a lift or a change in price that would also simultaneously cause a change or a lift in demand. For instance, it could be that during Christmas, price increases and also demand increases, right? But it's not that demand increases because of price, but it's just that they could simultaneously sort of correlate through this other variable. So if you're now a better data scientist, what you would try to do is you try to control for all of these variables, typically called confounders, which simultaneously affected the treatment or the pricing decision in your historical data, and also could simultaneously have a direct effect on the outcome. So you could add here the season indicator into your model, and maybe you would fit a better machine learning model that also includes the season indicator as an input. Now everything is much nicer because by including this, you are going to split the data into the data that came from Christmas and the data that came not from Christmas, and then locally in these data points you're going to fit a downward sloping curve, and so the coefficient in front of the price is going to be this negative thing, and now you're going to get a more meaningful answer. The problem that you might now start to face is that if you want to be sure that the coefficient that you fit in front of the price is the causal coefficient, is that you might need to control for hundreds or maybe thousands potential confounders, right? Especially if you're fitting a linear model, maybe you want to fit for non-linearities, and maybe you want to create non-linear features of a small set of variables. Or if you're in a big company where you did a lot of data collection, maybe you have a lot of features for the products that you priced, and so you want to control for all of those features. So then the question becomes a statistical question. You want to fit this very high dimensional model that controls for a lot of confounders, but all you care about is this coefficient in front of the price. And so typically you won't be able to estimate sort of this quantity over here very well, but the question is, can you still estimate this single parameter that you really care about in a fast sort of parametric rate? So that's one question that you might want to ask. I might need to estimate this quantity over here, this function f of x, of how the confounders affect the outcome, but it's not that I really care about this function over here. All I care about is this coefficient in front of the price. And we'll call the price also interchangeably treatment because it's a more general setup. So the question is, these are sort of like the auxiliary models that you need to fit. These are like the nuisance models that you need to fit in order to get a causal estimate, but you don't really care about. And so, maybe if this was a low-dimensional object that you could estimate at a root and rate, then maybe you just run your, standard machine learning algorithm, and you try to predict the outcome from both the treatment and the x's, and then you might get reasonable answers. But typically, this won't be estimable at a root and rate. And so the question is, how can you devise a better algorithm that estimates this at a root and rate while controlling for a very high-dimensional object? And so here's a solution that was recently proposed by a group of econometricians, many of them here at the econ department. That's typically referred to with the name as double machine learning. Okay. So what does double machine learning propose that you should do? It says, let's try to predict the outcome from all of these things that you're trying to control for, from all of the confounders. So here you're trying to build a predictive model, and you can use whatever predictive modeling pipeline you like. You can use any machine learning algorithm that you want to solve this prediction problem, which is just a normal regression. Similarly, you will try to predict the treatment, the price, from all of these things that you want to control for. And now the interesting part is that if you write the residual of the outcome, whatever you could not predict from the outcome, then this has a linear relationship with the residual in the treatment, which is whatever you could not predict from the treatment. Okay? And so in a final stage, you can just run a single-dimensional linear regression problem that regresses this unpredictable part of the outcome on the unpredictable part of the treatment. Right? And so this is the simple square loss minimization here. And the nice theorem is that as if you do these first two regressions on a separate sample, say you split the data, you run the first regressions on half of the data, and you run this last regression on the other half, then as long as these first stage regressions satisfy a root mean squared error rate that is quite slow, of order n to the -1/4, then your final estimate in this regression will behave as if you had a normal single-dimensional regression problem. So it will...
should be faster rate
yeah, at least that. But this, I'm saying it's as slow. It's a slow rate, but it should be at least as fast as n to the minus 1. Yes. So then this would behave as if you were just running a single-dimensional linear regression. So that means that the estimation error of this is going to be of order 1 over root n, and also importantly, it's going to asymptotically have a normal distribution, and so you can also do hypothesis testing for your final estimate theta as if you had a single-dimensional problem, right? Single-dimensional parametric problem. One of the reasons that you can get away with slow rates here and still get root n rates is this property of Neyman orthogonality that your final regression here satisfies. So if you take the derivative of this final loss, then this corresponds to what is known as a moment. And so your estimator here is an estimator that is based on finding a zero of a moment that satisfies this notion of Neyman orthogonality. And I'll describe later on, as we generalize this notion, what exactly it is. But this is the reason why you can get away with these rates. And then the other reason that you don't need to estimate to assume anything about your first stage models other than the mean squared error rate is that you do this sort of sample splitting. Right? So sample splitting and Neyman orthogonality together give you this very nice theorem. You can also, if you're really scared about sample splitting, maybe you have a few samples. There's also a better version of sample splitting where you fit these models on the first half of the data and predict on the other half, and fit on the other half and predict on the first half, and then you use all of your data in the final regression, which is called cross-fitting, and this would still have the same properties as this sample splitting estimator. So some remarks, in order to estimate this causal effect, which is this single coefficient that we were interested in, and at a fast rate, we had to estimate these nuisance functions, which were sort of like regression or prediction problems, and so we could use machine learning for that. One drawback of this theorem is that it was targeting an average treatment effect. So this would say, on average, if I change my price, how would the demand change? Many times in most of these motivating scenarios I mentioned in the first slide, we might be interested in personalized decisions, which means that we need to estimate a heterogeneous effect. So how does the price affect demand, conditional on a bunch of features that I observe of the customer I'm pricing or of the patient I'm treating. And so you don't just want to estimate an average treatment effect theta, but maybe most probably a heterogeneous treatment effect model or a function theta of x. So apart from using machine learning in order to estimate these nuisance functions that you don't really care about, you might want to also use machine learning and data adaptive estimation for also estimating this complicated heterogeneous effect function theta of x. So there are two reasons why you might want to use machine learning. Like by machine learning, I mean more like data adaptive estimation. It's because you might want to estimate more accurately your nuisance functions and be non-parametric, and also because you might want to estimate your heterogeneous treatment effect more accurately and also be non-parametric. So how would you alter the previous theorem in order to address this heterogeneity problem? You can do a very simple adaptation of the double ML algorithm and target heterogeneous treatment effects. And the simple adaptation is, instead of just minimizing with respect to a constant here, just minimize with respect to some hypothesis space theta of the square laws, where now instead of a constant we have any function that takes as input these features that you observe. Okay. And so you can also, and this sort of like now is a statistical learning problem. We just want to minimize these laws with respect to some hypothesis space, and we can also apply, our favorite machine learning pipelines. We can do cross validation. We can, apply our generalization bounds for whatever hypothesis space we have, and so on.
Sorry, this is fast for me. X is now W.
So yes, so I'm saying we're now controlling for both X and W, but we might want to use just X for heterogeneity. I am splitting now.
So you're splitting X into X and W?
Yes.
And the one that you want to keep is X?
Yeah, and the one that I want to keep for heterogeneity is X. The rest I want to still control for, but maybe I don't want to estimate heterogeneity with respect. So, and there were some papers that used this approach to estimate heterogeneous effects, where they analyzed this sort of algorithm for particular hypothesis spaces here. So for instance, the paper of Nye and Wager analyzed the case where theta is a reproducing kernel Hilbert space. In a paper we wrote, we analyzed the case where theta is a sparse linear function. So x is high dimensional and this is a linear function. But we only assume that only a few of the x's are relevant. And in another paper, we also analyzed the case where theta is represented by a random forest. Now, for these complicated hypothesis spaces, proving asymptotic normality is typically hard. So, for forests, we could do something, but in general, you wouldn't hope to prove some form of asymptotic normality, but you could at least hope to prove some sort of mean squared error of your final causal model. And this is exactly what these papers were showing. They were showing that the error, the mean squared error of the estimate in this final regression, in this final loss minimization problem, gets a second order hit from the errors in this first stage model. So this is sort of like the robustness that was also in the parametric case, where we were able to get root n rates for the final estimate as long as the first stage functions were n to the 1/4, and here there is the same thing is happening here. You can show that the mean squared error of theta is of the order of the oracle mean squared error that you would have gotten had you really known Q and P, plus a second order impact from the mean squared errors of Q and P that are coming from the first stage estimation errors. So you get this sort of robustness to the nuisance quantities. All right. So this was a first set of results that were showing such robustness of the final sort of causal model to estimation errors in the nuisance models that you didn't care about.
So just one thing, if W is now nothing, does this reduce to just regressing y onto x or not?
Not exactly, because you still run some form like non-parametric regression in the first two stages. Right? And maybe still, the confounding part is a harder function to learn than the heterogeneous effect part, right? So maybe you believe that the heterogeneous effect is a sparse linear function, but maybe the confounding effect is a denser function. So you're still going to get an improvement here. So this was also one motivating example in this paper. We're saying, maybe everything is high-dimensional linear, but maybe the heterogeneous effect is a simpler function to learn. It has fewer non-zero coefficients, and so you get a benefit from doing this. So let me show you a second example that has a very similar flavor. And this is the case where we now have binary treatments. So instead of having these continuous treatments that we analyzed in the previous step, though you could apply also the previous algorithm to binary treatments, but there is another nicer algorithm for the case of binary treatments. So when you're just trying to decide whether to treat or not, say in a personalized healthcare type of application, you still want to estimate what is the effect of the treatment based on some set of observational data. But again, if you forget to realize that your treatment in the observational data might be biased, so maybe you were treating more people that look like X, and maybe those people that look like X also have better clinical outcomes. And so you would be wrongly attributing those better clinical outcomes to the drug as opposed to these features that define this subgroup X. So if you want to estimate an unbiased estimate of the treatment effect, say the average treatment effect, you need to control for all of these variables that sort of describe this bias. So you need to control for all of the variables that might have entered into your treatment decision in the historical data. One way to do it would be a very model-heavy approach where you just try to predict the outcome y from both the treatment and all of these features that that you want to control for. This would be a direct regression method. And then once you learn such a model that tries to, that learns the conditional expectation of the outcome conditional on the treatment and all of the things you want to control for, then an unbiased estimate of the average treatment effect is just the average of the difference between the treated and the untreated, right? So you could apply your model that you learned and apply it for t equals 1 and apply it for t equals 0 and then take the average over the whole population. This is a very model-heavy approach because essentially what you're doing here is you're learning a model that learns, for instance, the mean outcome from the treatment population and then applies that model that you learn on the untreated population, because you're going to apply this function on both the treated and the untreated. And so you're doing some form of domain adaptation, and that might also perform poorly. Also, what you're essentially doing is you're extrapolating from the treated population to the untreated population based on a model, whatever model you used here to fit this regression. Right?
Here, the guarantees are in individual treatments or
Yes.
on the average?
Individual treatments, yes. So, right. So, okay. So another way to deal with this problem is to use what is known as inverse propensity weighting. It's a very most probably many of you know about it, which is to observe that if you divide the outcome that you observe for every patient or for every sample by the probability of that sample receiving the treatment that you observe, then this is a non-biased estimate of the outcome of that sample under of the counterfactual outcome of that sample under the every possible treatment. So this would be 0 if you didn't get that treatment, and this would be y divided by the propensity if you did get treatment t. And so in expectation, you're gonna sort of like get that the expected value of yi 0 is equal to the true potential, the true potential outcome, and the expected y of I1 is equal to the true potential outcome. So now that you have a non-biased estimate of both potential outcomes, which is, like what would have happened to exactly you if we treated you or we didn't treat you, then you can just take for every person the difference of these two potential outcomes and take an average of this difference over the whole population, and this would be a non-biased estimate of the average treatment effect.
How did you resolve the problem of not having a model to estimate PT at this point?
Yeah, so here, if you knew the propensity in the data, then here you wouldn't need to fit any model. So if you knew what policy was being deployed in the hospital, for instance, you would just use that. You wouldn't need to fit a model. But as you say, many times you would, and this is why this I'm saying is not a very model-heavy approach. But again, if you don't know the observational policy, then you need to fit a model for PT. And so you will have, again, a problem that estimation errors in PT are going to directly affect the accuracy of theta. And so if this was a non-parametric estimation or some high-dimensional estimation, you're going to get the same type of inaccuracy on your final estimate theta. Right? And so this is also not a very good approach because of this direct hit from the estimation error on P on the final estimate theta. Also, this is not a good approach because it also has high variance. Even if you knew the propensity, you're dividing by it, and so you're dividing a relatively large number by a relatively small number, so you get a high variance estimator. So one way to resolve the drawbacks of the two methods would be to combine them, and this is the doubly robust estimator that dates back to early work of Robbins and Rotnitsky and Zhao, where you basically fit both a propensity model and a direct regression model. So you try to predict the counterfactual outcome based on a regression model, but then you try to debias that. You say, okay, but whatever is not really well explained by the regression model, which is this residual, I'm going to do an inverse propensity correction to it. Right? And you can see that this is also so if either this has the doubly robust property, which means that if either H was a correct model or P was a correct model, then this Y is an unbiased estimator of the counterfactual outcome. And so this is why it's doubly robust, because you need only one of the two models to be correct. Okay? And you can see that here. Why? Because suppose that H was the correct model, then this difference over here in expectation is a mean zero difference. And so this whole quantity cancels out, and the effect of P on the counterfactual outcome is mean zero. Okay? So P does not really matter in the counterfactual outcome. Similarly, if P was the correct model, then this indicator here divided by this is going to be a -1, and so minus H plus H is going to cancel out, and all that you're going to get is back the inverse propensity model. But this is a better estimator because it has this doubly robust property. Also, it's a more efficient estimator because now you're dividing just the residual by the propensity, so you're dividing a much smaller number by the propensity, and it provably has a better variance than the previous estimator. And so now instead of taking the average of the inverse propensity counterfactual outcomes, you're going to take the average of these doubly robust counterfactual outcomes. The problem again is that here this was primarily targeting average treatment effects, and so how do you estimate heterogeneous effects? And there is an easy also adaptation of this algorithm for heterogeneous effects, where you construct all these doubly robust counterfactual outcomes, and instead of just taking the average, you minimize a square loss trying to predict the difference of these counterfactual outcomes from a function of the features x that you want to heterogeneity with respect to, and you minimize the square loss over some hypothesis space. And then in these papers, we could show that again, the mean squared error of your model theta over here gets a second order hit on the mean squared errors of the estimates of p and h that you did in these first stages. So you again have this robustness of the final causal model to estimation errors of these nuisance models that you need to estimate, but you don't really care about. And the intuition here is this doubly robust property that I mentioned before, and essentially doubly robustness has an intimate connection with this notion of Neyman orthogonality. They're not identical, but they're, for example, typically double robustness implies Neyman orthogonality. So again, deep down, the reason why you have this robust property is this Neyman orthogonality property of this final loss function that you're using here. And finally, let me give you an example from the literature on policy learning, which is a small tweak to the previous setup. So suppose that instead of trying to estimate the heterogeneous treatment effect, now you just want to find optimal treatment policies. So now what you want to say is, given the function, given the features x that I observe, do I want to treat or not treat this patient? So this is not a model that tries to predict the actual effect, but it's just a model that tries to predict will the effect be positive or negative, right? And then say, treat or not treat based on the sign of the policy. So if this is all that you want to do, many times you can bypass the whole modeling step and bypass estimating the actual heterogeneous effect and directly target this policy problem, right? And here's how you can do it using this sort of like doubly robust idea from the previous slides. So because we know that these doubly robust estimates are good estimates of its counterfactual outcome, we can now write a good estimate of what would be the value of any treatment policy. So now theta is not a model of the heterogeneous effect. Theta is a policy that maps the features to an indicator of whether I treat or don't treat. And the value for any such policy theta is take an average over your population of if you treat that sample, then you collect the counterfactual outcome from the treatment. If you don't treat, then you collect the counterfactual outcome from the non-treatment. So this is now your value function, and this is what you're trying to optimize. Optimizing this essentially means that you're optimizing this linear function of your policy theta, where the coefficient in front of every sample is the difference in counterfactual outcomes.
Do you sample split here?
Yes, in all of these you always sample split for the nuisance parts, or do cross-fitting. And again, there was this paper by Athe and Wager that says that the regret of your final policy here, so the difference between that final policy and the best the best policy within the policy space, if you knew the true value function, is of the same order as the oracle regret plus a second order effect of the nuisance estimation errors of the either regression model or the propensity model.
So here the y's are not random variables; they're expected values.
So the y's here are these exact quantities over here. They are random variables, and they depend both on the regression model and the propensity model and the real data yi. Right, so.
But you're not trying to maximize the expectation.
I'm trying to maximize the expected policy value, right? So you're taking an average of the policy value. But now I have a good proxy of what would happen to this particular patient if I treat or not treat, which is this, in expectation, this is the correct thing. And so this in expectation will be an unbiased estimate of the.
So the oracle is the one that's just minimizing the expected value.
Yes. Okay. And so this, all these prior works sort of led us to formulate a general version of all of these results, which we sort of call orthogonal statistical learning. And so here's the general setup. Sorry. You have a target model theta that is defined as the minimizer of some population loss function. But this loss function, crucially, apart from the model theta that you're trying to estimate, also depends on other models that you don't really know about, and which you also need to estimate from the data. Okay. So these are the nuisance models, and this is the target model that you're interested in. What you care about is achieving good oracle excess risk. So find given n samples, find the model theta hat, such that the difference between in the population loss and when evaluated at the true nuisance functions, the difference of theta hat and the minimizer is at most some rate Rn. So for instance, in the pricing example, this is the implicit population loss that you were trying to minimize, the square loss that depends on the direct regression model and the propensity model, and theta is your heterogeneous effect. In the binary treatment case, this was your population loss that again here depends on the regression model and the propensity model. And this is your target model that you're interested in. And in the policy example, this is the linear population loss that you were interested in, where again it might depend on these nuisance functions. Right? Now, why do you care about oracle excess risk? For example, here for the case of square losses, a good excess risk is going to imply good mean squared error because of strong convexity properties of the square loss. And here, oracle excess risk is essentially equal to the regret of your policy. Right? So all of the things that you're interested in here can be abstracted away to this oracle excess risk target quantity. Another reason why we want to formulate this as a generalization bound problem, as an excess risk problem, is because we want to reuse a lot of recent advances in statistical learning theory and in statistical machine learning that prove better generalization bounds for different hypothesis spaces. So by phrasing it as a sort of generalization bound problem, we're closer to being able to reuse all of this machinery that is recently being developed. The only problem is that most of this machinery is sort of targeting situations where you sort of know what your population loss, where you don't have this unknown nuisance function. So you're given some population loss that does not depend on any auxiliary quantities, and you can achieve some sort of like excess risk rate and many times you can also prove a minimax optimality. So most of ML theory addresses such questions. And as I said, this generalization bound can also imply several quantities that you might be interested in where you're doing sort of causal inference or policy evaluation. And so the question is, can we reduce our problem, which is the statistical learning problem with a nuisance component, to a standard machine learning problem, which is statistical learning without a nuisance component? And there's a sort of like, okay. The other, side advantages of focusing on excess risk as opposed to other quantities that people are looking in the, in causal inference and econometrics is that we typically, by focusing on excess risk, we do not require several stringent assumptions on identification of parameters of the model. For instance, if you're trying to estimate a model of heterogeneity that is a sparse linear function, if you want to do parameter recovery, you might need to assume some form of like a restricted eigenvalue condition. If you just want some generalization bound, you might not need to assume such a condition. And many times you can also prove results when you have misspecification. When you focus on excess risk, you can say, I might not, my true model of heterogeneity might not be in the model space that I'm optimizing over, but maybe I'll achieve good excess risk with respect to the best policy in the class.
Correct me if I'm wrong. So a lot of these papers, they do sample splitting because they care about doing inference. They want a symbolic normality result. For the individual effect, the heterogeneous individual effect, seems like it's really hard to get a symbolic normal result. Then maybe you don't need sample splitting. Then you uniform deviations and then.
We still need for the general theorem that we're going to show, because we want to sort of say that you can apply a generalization bound for a plug-in estimate as if your data were IID. If you've already fitted on the same data, then you don't have this IID-ness condition, and so it's not clear, what correlation among the data this nuisance estimate creates, and so you cannot really apply in a black box manner all of the statistical learning theory guarantees that typically assume IID data. Right?
But the data is still IID, just the test, the evaluation thing depends on a certain function of the data, right?
Yes.
So that's uniform deviation.
The data
We can
yes, let's take it offline. Yeah, and maybe you'll then need to do some sort of like you might still need some sort of like don't scare property for your nuisance estimates, right? But here with sample splitting you will only need a mean squared error guarantee for your nuisance estimate. So even that buys you something, right? So this is exactly to this discussion. This is the meta algorithm that we're going to analyze to reduce statistical learning with the nuisance component to normal statistical learning. We're going to split our samples in half, and on the first half we're going to estimate the nuisance estimates based on arbitrary, some arbitrary estimation method. Subject to that estimation method, achieving some form of mean squared error guarantee. And then we're going to plug in this first stage estimate into the loss function and apply any other ML estimator or any other estimator that you want that achieves good excess risk for the plug-in nuisance functions. Right? So it manages to achieve an excess risk for this loss function of Rn hat of theta. Right? So now once I plug in the G hat, this is a normal statistical learning problem. And you can apply any theorems that you want from statistical learning theory to this plug-in statistical learning problem. But of course, this is not what you really want. You don't want an excess risk on the plug-in nuisance function. You want an excess risk on the true nuisance function. So the main question that then you want to ask is how do these two relate? And can you show that this thing is of the same order as this plus second order effect from this? To be able to do that, we'll need to introduce this notion of Neyman orthogonality of the loss function. So to define the notion of Neyman orthogonality, we first need to define a directional derivative because we're going to try to understand derivatives with respect to these functions of our loss functions with respect to these sort of functions. And the directional derivative is the pretty standard thing. If you have a direction nu in this function space, you're going to define the directional derivative as the standard derivative when you're moving in that direction and when you evaluate this derivative at t equals 0. So this is the directional derivative, and then a loss LD is Neyman orthogonal if this cross derivative quantity is equal to 0. Right? So if the derivative with respect to your nuisance functions of the derivative with respect to the target function when evaluated at the true target model and the true nuisance model is equal to 0. The intuition of this condition is that small perturbations of the nuisance model around its true value do not change by much the gradient information that is in your loss for the target model that you're interested in. Right? So by slightly changing the nuisance functions, the first order condition roughly remains the same. And this is satisfied by all of the loss functions that we described in the first part of the talk. So for instance, for the square loss over here of the residual and residual, if I take a derivative with respect to theta, this is sort of like a derivative with respect to the output of a normal derivative with respect to the output of this function. So this is going to be just 2 times this quantity multiplied by this quantity. And then when I take a derivative with respect to a nuisance, say I take a derivative with respect to this, then all that will remain is this difference over here. But this difference is a residual which under the true nuisance model is mean 0. Right? And so this quantity is going to be equal to 0. Right? And so this residualization of the treatment was really what made this loss function be Neyman orthogonal. And so one of the main theorems that we proved was that if a loss is orthogonal and strongly convex, so these types of square losses, and satisfies several smoothness properties, then the oracle excess risk that we care about is indeed upper bounded by this plug-in excess risk plus a second order effect from the first stage estimation errors. Here we're going to have like to the fourth rate, this is really a square because we assume the sort of root mean squared error rate for the first stages, and these are typically square losses, so that's why you get to the fourth. But for the case of parametric functions theta, this the rate that you should expect is like for the square laws would be 1 over root 10, and the rate that you should expect from then the rate that you would need here is n to the minus 1/4.
So if you assume that if you take the first two derivatives against g vanish, can you put a 6 up there if you want?
Yes, you can.
Okay.
But it's not clear how you would achieve the second order Neyman orthogonality. We had one paper where we were basically proving the existence of such a second order Neyman orthogonal for this particular setup of residual on residual. It's not clear that though that thing that we did there was more like a moment-based estimation, and it didn't really correspond to the gradient of a loss. So it's not clear how you do heterogeneous effect. So yes, you can, but the conditions of the existence of this second order Neyman orthogonal are more stringent. Many times you can't even have them. But it's sort of like easy to achieve first order orthogonality by just adding a debiasing term, typically. Okay, so I'm not really going to talk about all of this. I think I'm also sort of running out of time. The other result that we have is for the case where you don't have strong convexity. So the case, for example, of policy learning, where our loss was linear, so it was not strongly convex. Then if we make a slightly stronger assumption of universal Neyman orthogonality, which basically says that this cross derivative is 0 not only at the true theta, but at every theta, then we still get this second order dependence from the first stage estimators. But here, because we expect some sort of like, slow rates, 1 over root n rates, we get the square and not the fourth moment. So with that, I think given that I'm out of time, I would just like to stop here and just mention some takeaway points. So machine learning is useful in causal analysis for estimation of nuisance models and for estimation of heterogeneity. Neyman orthogonality is a concept that can improve machine learning theory for causal problems, so you can show robustness to nuisance errors, and many times you can even show asymptotic validity of the confidence intervals. And on the other hand, focusing on excess risk in causal problems, we can get more robust theorems that do not make stringent assumptions on identification, and enable the use of recent advances in statistical learning theory for fitting causal models that belong to complex hypothesis spaces. That's it. Thank you very much.